Imagine, if you will, standing beneath a vast, dark sky, far from the city lights. A celestial wanderer drifts into view, a cosmic ice sculpture carved by the chill of space and kissed by the distant sun. It's a comet, of course, a breathtaking spectacle with its luminous head and ethereal tail stretching across the inky blackness. For centuries, these visitors from the outer reaches of our solar system have captivated us, inspiring awe and wonder. But for astronomers, observing these majestic comets has always presented a peculiar, almost whimsical riddle. Many comets, as they draw closer to the sun, develop a truly radiant, almost otherworldly green glow around their heads. It's a vibrant, unmistakable emerald hue, shimmering like a cosmic jewel. Yet here's the odd part: that striking green color never, ever makes it into their tails. No matter how brightly the head glows, the tail remains stubbornly absent of any green tint. It's a detail that might seem minor at first glance, but for anyone who has gazed upon these celestial travelers or meticulously studied their composition, it's a glaring inconsistency. Where does the green go? Why does it just stop? This wasn't merely a fleeting observation. Astronomers have never, in all their recorded history, documented a comet with a green tail. This enduring mystery, this cosmic conundrum, went unsolved for an astonishing 90 years. 90 years of observations, theories, and head-scratching. The first whispers of a potential answer began to emerge in the 1930s. Researchers, peering through their telescopes and analyzing the light spectrum of these comets, started to suspect a particular chemical could explain the whole enigmatic display. They pointed to something called dicarbon. Now, dicarbon isn't a substance you'd typically encounter in your everyday life. It's a chemical made of two carbon atoms bonded together, but it's incredibly reactive and unstable in Earth's atmosphere. However, in the extreme environment of a comet, things are different. As a comet approaches the sun, the ice and dust on its surface begin to sublimate, turning directly into gas. This gas often contains organic matter, the building blocks of life, albeit in a very basic form. When this organic matter is exposed to the intense ultraviolet radiation from the sun, a fascinating chemical reaction occurs. Dicarbon is formed. And it's this very dicarbon that, when excited by sunlight, emits light in that distinctive, brilliant green wavelength. So the theory went, dicarbon was indeed responsible for the comet's dazzling green head. It made perfect sense. But the mystery of the missing green tail persisted. If dicarbon was the source of the green, why didn't it continue to glow as it was swept back into the long, flowing tail by the solar wind? This is where the second, equally crucial part of the dicarbon theory came in. Scientists hypothesized that while sunlight created the dicarbon and made it glow, that very same powerful sunlight also destroyed it. The idea was that the dicarbon molecules simply didn't survive long enough, didn't travel far enough from the comet's head before the sun's relentless radiation broke them apart. It was a compelling idea, a neat explanation for a long-standing riddle. Yet for all its elegance, it remained a theory, unproven for nearly a century. The challenge was immense. How do you prove something that occurs in the vacuum of space, with volatile chemicals, under the intense glare of a star, right here on Earth? It required ingenuity, precision, and a healthy dose of scientific daring. Then, in 2021, the universe, through the hands of dedicated scientists, finally offered its definitive answer. Researchers embarked on an extraordinary experiment, aiming to recreate the conditions that lead to the birth and, crucially, the demise of dicarbon. This was no easy task, as dicarbon is notoriously volatile and exists only in extreme places, like the heart of a stellar furnace or, perhaps, the head of a comet. In what was truly a world first, these scientists managed to synthesize dicarbon within the controlled environment of a laboratory. They then carefully introduced this newly created dicarbon into a vacuum chamber, meticulously simulating the frigid, near-perfect vacuum of space. Within this chamber, the dicarbon was brought into contact with gas and, most importantly, powerful lasers. These lasers weren't just for show. They were designed to mimic the exact kind of solar radiation that dicarbon encounters when a comet races towards the sun. And the results were conclusive, almost dramatic. The lasers, acting as miniature sunbeams, effectively ripped apart the dicarbon molecules. They observed the dicarbon breaking down, disintegrating, before it could travel any significant distance. The experiment provided the undeniable proof. The sun's radiation, while initially exciting the dicarbon to produce that stunning green glow, simultaneously acts as a destructive force, tearing the molecules apart before they can be swept back into a long green tail. It was the elegant yet destructive secret of the sun. So, after 90 years, the mystery of the green heads and the absent green tails was finally solved. It wasn't some exotic alien intervention or a complex gravitational anomaly. It was the elegant yet relentless interplay between a simple chemical compound and the powerful radiation of our own sun. It's a beautiful reminder of how even the most subtle observations in the vastness of space can lead to profound scientific journeys, culminating in a deeper understanding of the universe around us. It teaches us that nature's processes, though seemingly complex, often reveal themselves with a captivating simplicity once we find the right way to listen. What other cosmic mysteries do you wonder about? Share your thoughts in the comments below. And if you enjoyed this journey into the secrets of comets, consider following for more stories from the frontiers of science and discovery. Until next time, keep looking up.